Okay, so without further ado, let's start our class here. So today we will learn about module 8. Okay, which is in this module here, you will learn about stack and subroutine. Okay, so in this module, okay, you will learn about stack, what is a stack pointer, how to obtain the stack pointer, how to initialize the stack pointer, and why we're going to use the stack pointer as well as the subroutine, how to call a subroutine and how to return from subroutine. Okay, so let's look at the stack. Right, stack is a section of RAM used by the CPU to store information temporarily. Okay, which is you're going to store the data or you're going to store an address. The CPU needs this storage because there are only limited number of registers. Okay, as you can recall, the number of registers that we have in Atmega 32 is the total is 32 only, which is you have the 32 general purpose register. So that number not enough if you're going to store many data or many addresses. Okay, so one of things that we can use is we can use the stack in order to store the data and addresses temporarily. Okay, so usually a stack is a last in first out, which is a LIFO lah. Buffer containing a number of data item usually implemented as a block of n consecutive byte, word or long word in a memory. So the stack use a last in first out. Okay, and then the address of the last data item placed into the stack is pointed by the stack pointer. Okay, so you have a stack and then you have the stack pointer. The stack is the data that you store temporarily, while the stack pointer is the address where you store that data inside of your RAM. Okay, that stack and stack pointer is two different things. One is the data that you store inside of your RAM, and the other one, the stack pointer, is the location of the address where you store that data. So the application of stack is temporary storage of variables. Okay, you can store variables, you can store data, you can also store a program addresses, and the last one here, to communicate as a communication with the subroutines. Okay, if you're going to use the subroutine, then you need to use the stack. Okay, so now we are going to see how we are going to access the stack in the AVR. Okay, since the stack is a section of RAM, so it needs a register inside the CPU to point to it, which is called as a stack pointer register. So stack pointer register is a register that contains the address of your stacks. Okay, the stack pointer is 16-bit wide and is implemented as a two register that are stack pointer low and stack pointer high. Okay, so since kita punya stack pointer is 16-bit, 16-bit, so you need to divide it by 2 lah. One is stack pointer low, and the second one we call it as a stack pointer high. Okay, so inside of this pointer low, address of your stacks. Okay, the stack pointer must be wide enough to address the RAM, those AVR which is greater than 256 bytes of memory. The stack pointer is made of two 8-bit registers, which is SPL and SPH, while the AVR that have a less than 256 bytes, okay, the stack pointer only made of the SPL. Okay, there are two types of operation involving in the stack pointer. Okay, one is push, the other one is pop. Okay, the push instruction used to store of the CPU information, okay, to your stack, while pop is used to obtain or to retrieve back the data from your stack to the CPU. Okay, so usually, okay, sekejap ya. Okay, so this is our data memory. Okay, so data memory can be divided into three parts: GPR, IO, and RAM. So your stack should be around this RAM here. Okay, so stack pointer must pointed to this location, which is inside of your RAM. Okay, to what we call here, to store the data, okay, from CPU to your stack, okay, what you need to do is you're going to use the push instruction. Okay, push to store a data to your stack. Why? To retrieve back the data from this stack and put it to your GPR or to your CPU. Okay, so we are going to use the pop instruction. So the stack only have two instructions. One is push to store a data from GPR to stack, while the second one is pop to retrieve the data from stack and put back to your GPR. Okay, so let's look at the how to push the data to the stack. Okay, so okay,
Sir, we can't
yeah.
hear you.
Can you hear me now?
Yeah.
Okay, kat mana tadi kita stop? Kat mana kamu tak dengar tadi? This one ya, how to push
I
the
think
data to
this whole page.
this
This
whole
page.
page or the
Yes.
previous page.
No, this page.
Okay, this page. Okay, so now we're going to what we call here to push a data to your stack. Okay, so the stack pointer always point to the top of the stack. Maksudnya kat sini, okay, so this is your RAM. Okay, we have a RAM. Okay, let's say lah, this is your data that you put to your stack. Okay, this is your stack data. Okay, so what happened is the stack pointer always pointed to the top of your stack. Okay, so since this is your data, so this is your stack pointer pointed to the top of your stack. Okay, next, as we push the data to the stack, okay, whenever you want to put the data to your stack, the data are saved where the stack pointer point to. Okay, so now stack pointer here point to this address. Okay, let's say lah this is 085F and this is 085E. Okay, now you're going to put the data to your stack. So what happened is the stack pointer, okay, the stack will store here inside of this 085E address. And what happened to your stack pointer? The stack pointer will be decremented by 1. So now the stack pointer point to new address which is 085T. Okay, that's why the stack pointer is decremented by 1. Okay, so in other words, the stack pointer is decremented whenever the data is pushed onto your stack. Okay, every time you use the push instruction, okay, the stack pointer will be decremented by 1. Okay, so to push a register a data to your stack, okay, we are going to use the push instruction. So this is what we call here. So this is the instruction. Okay, push RR means that you're going to take the value from RR and put it to your stack. so for example here, okay, you are going to store a value of R10 to your stack pointer, to your stack. So what you're going to do is you just use this instruction, push R10. So any value from R10, so any value inside the R10 will be stored into your stack. And at the same time, the stack pointer will be decremented by 1. Okay, this is how you're going to put a data to your stack. Okay, next, we are going to retrieve the data from the stack, okay, by using the pop instruction. Okay, so popping the content of the stack back into the given register is the opposite process of pushing. Okay, so whenever you do the pop instruction is executed, the stack pointer is incremented and the top location of the stack is copied back to the register. Okay, so what happen is, dia macam ni lah. Okay, now you're going to retrieve the data. So this is the data inside of your stack, for example. Okay, so this is 085F. This is 085E and this is address 085D. Okay, let's say lah this is your stack pointer. Okay, so now you're going to execute the pop instruction. Okay, let's inside of this 085D you have AB data. Okay, so you're going to use the pop R10, for example. So what happen is, okay, so this stack pointer here will be incremented by 1. So initially your stack pointer point to 085C. Okay, then it's incremented by 1. So now it pointed to 085D. So this value, okay, AB will be stored to this R10. So after you execute this instruction, R10 now have AB. Okay, so the stack pointer is incremented and the top location of the stack is copied back to the register. Okay, so because the stack is used the last in first out, okay, so the last data that into your stack will be the first data that coming out from the stack. Okay, so to retrieve a byte of data from stack, you can use the pop instructions. So this is the syntax of pop instruction, which is pop RR. RR is your GPR, can be from R0 to R31. Okay, for example here, you're going to copy the value R16 from stack pointer. Okay, you're going to take the value from stack to the R16. So you just use the pop R16. So whatever data from this stack will be stored to your R16. Okay, so that is a pop and push instruction. Ada soalan tak sampai sini? Okay, if no question, next we are going to see how to initialize the stack pointer. Why we need to initialize the stack pointer? Okay, so this is the reason why we are going to initialize the stack pointer. Whenever the AVR is powered up, okay, the stack pointer register contains the value 0. Okay, so every time you power up your micro P, every time you switch on your micro P, all the value inside the IO register, regardless lah stack pointer ke, you have port B, port C, DDRB, DDRC, all those things here have value 0. Okay, which is when SP have value 0, it will be pointed to address of R0. Kenapa R0? Okay, because if you recall back, okay, saya contoh. Okay, so this is your data memory. Ingat balik, this is your data memory. Your data memory can be divided into 3 types, which is GPR, IO, and RAM. Okay, so your stack pointer is around inside of this IO. So since SPL and SPH is 0, 0, the value here is 0, 0. So what happened is the stack pointer now point to address 0, 0. Okay, so you recall back. Okay, so this is the memory address of your data memory. It is starting from 0, 0, 0, 0 until your RAM end. Which is, what is your RAM end? Siapa boleh bagi tahu? What is the end address of your RAM? Okay, 085F. So what happened here is, since the stack pointer point to address 0, 0, so it point to this address here. So stack pointer point to this address 0, 0, 0, which is your R0 kat situ, which is wrong lah. Okay, by right, the stack pointer must be inside of your RAM, cannot be in the DPR or in the IO. It should be pointed inside of your RAM. Okay, so since in LVR, the stack grow from higher memory location to the lower memory location. Okay, so it is a common to initialize your stack pointer to the uppermost memory location. Okay, so now instead of this stack pointer point to this address 0000, you need to initialize so that the stack pointer point to the uppermost memory of your RAM, which is your RAM end. Okay, so the stack pointer should be point to address 085F dekat sini. This is the uppermost memory location. Okay, so how to do that? Okay, so we need to initialize lah. How to initialize this one? So we need to do some coding, some programming. Okay, so recall back, the stack pointer is made of 2 registers. Okay, you have a stack pointer. Stack pointer is 16 bytes. So since it is 16 bytes, you can divide it to, into 2 bytes, which is high byte and low byte. Okay, so SPL is for low byte and SPH is for high byte. So now we are going to put 085F to this SPL and SPH, so that our stack pointer point to address 085F. So this is how you are going to initialize the stack pointer. Okay, so to initialize the stack pointer, okay, you can use this instruction lah, load I. Okay, R16. Okay, the first number that you're going to put is 5F. Okay, 0x5F. And then this number here, you are going to store to your SPL. So by using the out SPL R16. So after you execute this instruction, so SPL now point to address 5F. Okay, next, you are going to 08 to your SPH. So how to do that? So by using the load I R16 O0x08 and then out SPH R16. So what happened here? SPH, after you execute this line here, SPH will have value 0, 8. So automatically your stack pointer now point to address 085F. Okay, so every time you see this 4-line coding here, so you know that this is to initialize your stack pointer. Okay, just asking, can we use the LDI SPLOX5F? Cannot, because LDI only used for general purpose register only, which is only valid for from R16 to R 31. Okay, so you cannot use the load I SPL 0x5F. So kena masuk dulu ke dalam you punya general purpose register, and from that general purpose register you send that value to your IO register. Okay, so this is an example show the stack and stack pointer and the register used after the execution of the each instruction. Okay, so let's go line by line for each of this program here. Okay, first include empty2def.inc. So means that you are going to include this file here to your program, and then you origin your program at address 0, and this for load I R16 high ramen out SPH R16. Okay, sometimes the best way to initialize your stack pointer by using by writing this instruction here. Okay, instead of you write something like this, load I R16 OX5S and then out SPL R16. So better we put something like this. Okay, which is load I R16 high ramen. The value of the high from this ramen you put to SPH, and the value of low ramen you put to SPL. Because why? Because if you take this program and put to another chip which is Atmega 64, okay, and then the ramen will be different. Okay, for Atmega 32 the ramen is 085F lah, but for Atmega 64 the ramen is another address. Okay, if you like tulis macam ni, so what happen is when you put the same program to another chip which is Atmega 32, then what happen is your stack pointer initialize at this address 085F instead of the RAM and the last address of your Atmega 64. Okay, so to be safe, better we initialize the stack pointer by using these 4 instructions here. Okay, so this is how you're going to initialize the stack pointer. Okay, next, LDI R31 0. So what happened here is R31 you put with 0, and then load I R20 0x21. So R20 now will have 21, and load I R22 0x66. So what happened here is R22 sama dengan 66. Okay, so for this kind of program, because we are going to use the stack pointer, so I just draw my data memory. Okay, so this is my data memory. Okay, so the first line here, so what happened is after I execute this 4 instruction here, my stack pointer point to this address, okay, which is your RAM N. Okay, so this is your IO, this is your GPR. Okay, now load I R31 with 0. So R31, so this is my R31. The value is 0, 0. And then I load immediate R20 with 21. So what happened is, let's say this is my R21. So R21 now we have, R20 sekarang ni akan ada value 21. And then load I R22 with 66. So let's this is R22. So R22 will have 66 kat situ. Okay. Next instruction is push R20. So what happened here is, okay, I take the value from R20, which is 21, and put it to my stack. Okay, so this is my stack. So R20 value 21, I put to my stack. So now the stack now have the 21 value. And what happened is my stack pointer now decrease by 1. Okay, dia tunjuk dekat address 085D. Okay, so this is my stack pointer after I do this push instruction. Okay, next I push another one, push R22. So what happened is value from R22 is 66. I put to my stack. Okay, and my stack pointer now decrease by 1. So my current stack pointer point to new address which is 085C. Oh, sorry, this is E. This one is E. Okay, and this is D. Okay, and then load R20 with 0, load R22 with 0. So what happened? So R20 now will have new value which is 0. R22 also got value 0 after I do this instruction. Okay, next, pop R22 means that I want to retrieve the data from the stack and put it to my R22. So what happened is R22 will have the value. Okay, what is the first? Okay, what is the last data that I put to my stack, which is 66 lah. Okay, so 66 will be load to R22, and my stack pointer increment by 1. So my stack pointer now, instead of pointed to 085D, now it point to 085E. Okay, so I erase this one. So stack pointer sekarang ni point to this address. Okay, then I pop again R31. So now because this one here already been retrieved, so the next data that I'm going to retrieve from the stack is 21. So I take this 21, put to R31. So R31 will have 21, and stack pointer is incremented by 1. So stack pointer now point to address 085. Okay, so this is the what we call the summary lah. Okay, what happened for each of the for each line of the previous program. Okay, so this is after you initialize the stack pointer. Okay, so stack pointer point to this address 085F, which is your RAM end. And then this is after you load R22 with 66. So R22 now has 66, R21, R20 got 21, R31 got 0, stack pointer 085F. And then you push R20. So what happened is okay, so value from R20 you put to your stack. Okay, so 21 copied to your stack. Now the stack pointer decremented by 1. So that's why the stack pointer point to 085A. And then you push another one to R22. Okay, push R22 your stack. So what happened is value 66 from your DPR put to your stack. And then the stack pointer decremented by 1. And then you load the data to R22 and R20 with 0. Okay, so stack pointer masih lagi point to 085D, while this is the value still inside of your stack. And then after that, you're going to retrieve the data from the stack and put it to R22. So what happened is value here R66, you put to R22, and your stack pointer incremented by 1. So now the stack pointer point to address 085A. Okay, by right, the value of 66 still inside of this RAM. Okay, masih lagi ada dekat dalam RAM ni, dekat alamat 085A. Okay, it not erase, tak jadi kosong. Okay, then you pop another one, pop R31. So what happened is you take the value from okay, from the stack, which is 21, and then put to your R31, and at the same time, your stack pointer incremented by 1. So the current value of your stack pointer is 085F. So by right, 66 and 21 still there. Masih lagi ada dekat this address. Okay, so this is how the push and pop instruction works and how to initialize the stack pointer. Any question? Ada soalan tak? Okay, Lee Wanting asking that is it a must to clear the GPR before popping? No need. Okay, you can. Okay, you no need to clear the GPR before you pop the data. Okay, because why? Because even though you not clear the GPR, the value from the stack will be replaced to your GPR. Will be saved to your GPR. So no need to clear the GPR before you popping. Okay, so this is another example. Okay, you see here. Okay, this is the program. Okay, so the first 4 line here used for initialize the stack pointer, and then after that you load the value 10 to R20, 20 to R21, and 30 to R22. Okay, so let's look line by line. Boleh tak dia play? Okay, so you initialize your stack pointer. Okay, currently your stack pointer point to this address. Okay, because this is the start of your program, your stack pointer point to address 0000. So now you're going to initialize your stack pointer so that your stack pointer point to the last address of your RAM. Okay, so now it goes to here, which is hi Rayman. Kalau you recall back, okay, so this is your Rayman 085F, and then you can divide it to 2 byte low and high. So now you put the 08 to your stack. Okay, so this is your stack pointer. Okay, now initially the stack pointer value is point to address 00. Sekarang ni you put 08 to your SPH. So what happened is the stack pointer point to address 0800. So that's why the stack pointer is somewhere around here, because you not finished initialize the stack pointer to your RAM end yet. Okay, and then you initialize again, and then out to SPL R16. Then after that, the stack pointer point to the last address of your RAM end. Okay, and then next, you load this value to R20, and then load the second value to R21, and load 30 to R22. So this is okay. So all the changes now can be seen inside of the register here. Then you're going to push R20 to your stack, which is 10 here. You're going to push to your stack. So what happens is, okay, value 10 you put to your stack, and stack pointer is decremented by 1. You push again R21, which is value 20, put to your stack, and stack pointer decremented by 1, and you push, and then after that you push once more R22 to your stack, which is 30 now, put to your stack, and the stack pointer decremented by 1. Okay, next, after that you're going to pop the value. Okay, pop the value to R21. So this 30 you put to R21. Okay, by right the 30 is there lah, masih lagi ada dalam you punya this address here. Okay, and then after that you pop to R0. So this value will be copied to R0, and last one here you pop to R20. So this value will be copied to R20, and the stack pointer is incremented by 1 every time you use the pop instruction. So this is how the push and pop instruction works. Okay, any question up until here? Ada soalan tak sampai sini? Okay, if no question, okay, next we are going to look at the next slide, move to the next slide, okay, which is the stack pointer upper limit. Okay, so as mentioned earlier, we can define the stack anywhere inside your RAM memory. Okay, you can put your stack pointer anywhere inside your RAM except inside the I/O register as well as the GPR. Okay, so your stack pointer can be anywhere inside the RAM only. In AVR, the stack can as big as its RAM. Okay, so note that we must not define the stack in the register, which is your GPR, nor in the I/O memory. Okay, so you only need to initialize your stack so that it is inside of your RAM. So the stack pointer must be set to point above 60. Okay, kenapa lebih daripada 60? Because the starting address of your RAM is starting at address 0060. The stack content is important as it used to store information when calling a subroutine. Okay, the stack overflow will occur when the content of the stack is exceeded the upper limit. Okay, it's something like this lah. Okay, so this is your data memory. Okay, so GPR, I/O, and this is your RAM. Okay, let's say lah you mistakenly initialize your stack pointer to address 0061. Okay, so this is 0060. Okay, so what happens is when you push, the stack pointer now point to address 0060. And when you push again, so what happened? The stack pointer now inside of your I/O register, which is exceeded the upper limit. So that's why you need to initialize your stack pointer, okay, at the end of your RAM here, which is your RAM. And in order to avoid the stack exceeded the upper limit. Okay, so this is the stack pointer upper limit. Okay, ada soalan. We have finished the stack pointer. Now we are going to see the subroutine. Ada soalan untuk stack pointer. Stack pointer and stack. Okay, if no question, then good. So now we go to subroutine. Okay, so subroutine. Laser pointer. Okay, so subroutine is a sequence of usually consecutive instruction that carries out a single specific function or a number of related functions needed by calling a program. Okay, so this subroutine can be called from one or more locations in program. Okay, why we going to use the subroutine? Because we are going to use the same set of the instructions sequentially. Okay, means that you're going to call the same instruction over and over. So this subroutine actually slightly different from branch and jump. Okay, that you will learn in the previous chapter, in which branch and jump will never come back to the place next to the instruction after the jump happen. Okay, everything you jump, then you go to that place, and then you never return to the instruction that you previously jump. But subroutine, once it go to the subroutine, or once it jump to your subroutine, and okay, so here let's say lah. Okay, now you have a program, and then you call the subroutine. So what happens is you jump to your subroutine, do the program, do the task inside of your subroutine, and once it's finished the subroutine, okay, it will return back to the next instruction after you call your subroutine, and then you continue the program again. Okay, so that is the difference between jump or branch and subroutine. Once you jump, you cannot go back to the place that you jump. The second one for the subroutine, when you go to the subroutine, you finish all the tasks inside the subroutine, then you can return back to the next instruction after you call the subroutine. So when a subroutine is called, the processor first save the address of the instruction just below the call instruction to the stack, and then transfer control to that subroutine. So that's why the CPU know where to return back once you call the subroutine, because the next address, okay, of this next instruction here already been stored into your stack after you use the call instruction. Okay, so for the subroutine, we have two instructions that you need to know. The first one here, we call it as a call instruction. The second one is as RET instruction. Okay, so for the call instruction, this one here used to call to subroutine. Okay, so this call instruction call to a subroutine within the entire program memory. So you can use an entire program memory. There is no limits. Okay, the return address, which is to the instruction after the call, will be stored onto the. Okay, when you call the subroutine, the next address, which is the return address, will be stored to your stack, so that after you execute the RET instruction, the CPU will take back that address that been stored to that stack and return back to the instruction after you call that subroutine. Okay, so this is the operation, and this is the syntax of the call instruction. Okay, you have call K. K is your memory address or program memory address. Okay, for example here, so you move R16, R0, and then call check. So what happened is, before you go to subroutine check kat sini, so you will save the address of this NOP instruction to your stack, and then after that you go to this check subroutine, do this task, and every time you see the RET, so the CPU take back the address that you stored at that stack, and what happened is it will return back to this NOP instruction. Okay, next we have a RET instruction. When the execution of the function is finished, the RET instruction at the end of the subroutine is executed. The address of the instruction below the call is loaded to your program counter, and the instruction below the call instruction is executed. Okay, so this is the RET instruction. Okay, RET stands for return from subroutine. The return address is loaded from the stack after you execute RET instruction. So this is the syntax. So RET. Okay, so this is the same what we call here. So this is the example. Okay, so you move this value to R60 and then call check. So before you call check, you save the address of NOP to your stack, and then after that you go to this check, do this compile CPI, and then do the branch EQU here, and then after that, if you execute the RET, so what happened is the address that you stored inside of your stack will be loaded to your program counter, and then the CPU know that you're going to return from subroutine and execute this NOP instruction. Okay, so the role of stack inside of the subroutine is this stack is used to temporarily store address. Okay, previously kita tengok the stack is used to temporarily store data, but now we are going to temporarily store address when the CPU execute the call instruction. So this is how the CPU know where to resume when it returns from the call subroutine. So hence, you need to be very careful lah when manipulating the stack content. Okay, for AVR whose program counter is no longer than 60 bit, the value of the program counter is broken into 2 bytes, okay, which is the lower byte is pushed to your stack dahulu and then followed by higher byte. Okay, so every time you're going to save the address, contohlah, okay, so this is your address. You have an address. So this is the address contoh 0844. Okay, so every time you going to store the address, you put 44 dahulu to your stack and then followed by 08, and then the stack pointer will incremented by 2 lah kat sini because you have 2 bytes. Okay, for AVR whose program counter is longer than 16 bit but shorter than 24 bit, the value of the program counter is broken up to 3 bytes. Okay, the lower byte is pushed first, then middle byte, followed by the higher byte is pushed. Okay, so this is the reason why you're going to use the subroutine. And then instead of call instruction, we have a RCALL, sama juga lah dengan jump. You have the RJump, IJump. So call instruction also have the same instruction lah, which is RCALL stand for relative call, ICALL for immediate, not immediate, indirect call. Okay, so this is a RCALL, relative call to subroutine. Okay, and then ICALL is indirect call to subroutine. But usually we use only the call instruction. Okay, so let's look at this example here, how the subroutine works. Okay, so this example here is used to count up from 00 to FF and then send the count to the port B. Use one call subroutine for sending the data to port B and another one for time delay. Put time delay between each issuing of the data to port B. Okay, so this is your program. So you include the mc2def.inc file and then def count equal to R20. So what happened here? Apa yang berlaku kat sini in this instruction here? Can you tell me what happened? Dot def count equal to R20. Anyone? Siapa nak tolong? Okay, so this instruction here, okay, you label your R20 as a count. Okay, you name your R20 as a count. So every time you see the count, means that is belong to R20. Okay, then origin zeros means that your program will be started at address 0000. That's why lah, the first line here, load IR16 high remain is started at address 0000. If you put .ord OX200, for example, so this line here will be started at address 200 inside of your program memory. Okay, so this is the first line, load IR16 high remain, out SPH R16, load IR16 low remain, out SPL R16. So what happened here? So this 4 line here, you use to initialize your stack pointer, so that your stack pointer point to address 085. Okay, after you initialize your stack pointer, so stack pointer now point to this address. Okay, 085F, 085E, and then you have a 085D. Okay, so now you initialize your stack pointer to 08. 5F. And then load I count 0. So what happen here is R20 sama dengan kosong. Okay. Next, call display. Okay, you see here, call display. So what happen is, before you go to the display subroutine, okay, you need to store the next address, which is jump back to your stack. Okay, so this is the address 0007. Okay, so you store what number that we're going to store here, because this is a okay, 0007 is this is a low byte and this is high byte, because this RAM here is 8-bit size. So what value that you're going to store? Is it 00 dahulu atau 07? Okay, we put the 07 and then stack pointer incremented here, and then we store the 00. After that, the stack pointer decremented here. Okay, then after that, you go to the display subroutine. So where is my display subroutine? So this is the display subroutine. Increment count, so you increment like R20. Out port B count, so you send the value from count to port B, and then call delay. Okay, so this is a call delay. So you call again. So what happened here is, before you go to delay, you need to store this address to your stack. Okay, so previously kita dah ada macam ni. Okay, I lukis kat sini lah. 085F 085D E D085C, and then D is a 085B. Okay, so currently we have 0700 inside of your stack, and stack pointer point to this address here. So now you call the delay. Before you call the delay, you need to store the next instruction, which is this RET 000C to your stack. So now we put the 0C first, the low byte to the stack, and then followed by high byte, and then the stack pointer will decremented by 1, 2. Okay, then after that, barulah you go to the call delay. So this is the call delay subroutine. Do this thing, load I RCTOSFF. Again, no operation, decrement R16. If the R16 not equal to 0, so you go again here, and then until R16 equal to 0, then you go to this RET. Okay, so when you go to this RET, what happens is the program counter, okay, will take this address and put it to the program counter. So the program counter now got the 00C address. So now the CPU know, okay, we need to return to this address 000C. Okay, once it's returned to this address 000C, then the RET instruction is called again. So what happened? Okay, tadi stack pointer kita dah point to here. After you return, it increase you take the address to your program counter, and what happened is the stack pointer is incremented by 2, and then next you have the return again. You execute the RET instruction again. So what happened is you take this value, this address, put to your stack program counter. Then what happens? Stack pointer now point to here. Okay, so now program counter show that it's going to address 0007, which is here, and then it will execute the jump back, which is yang ni, call again the display, and it will keep repeating. Okay, so this is the summarize of what happened before and after the call display. Okay, before the call display instruction is executed, the stack pointer point to the address. After you call the display subroutine, stack pointer is incremented and point to address 085D, and then the address of here, sorry, rjump back is put, okay, is saved to your stack, which is 0007, and then you call again. What happens is you take the next address of the next instruction after you call the delay, which is 00C, put to your stack, and the stack pointer now point to this address, and then you execute the RET. So what happens is the value, okay, this value here, you put to your program counter, and then the stack pointer is incremented by 2, and then by right, this value here still there, 0000C masih lagi ada dekat sini. Okay, not erase, not 0. Okay, and then you call the RET again. So what happened? So you take this address, put to your PC, and the stack pointer is incremented by 2. By right, the value masih lagi ada kat sini. Only the stack pointer now point to this address 085F. Okay, any question? Ada soalan tak?
Sir, can you go back one slide before?
Okay.
The
This one?
.org, yeah, this one. The .org 300, does that, will the system read that one? Because it calls delay, right? The delay directly skip the .org.
Okay, this one here, sebenarnya, this one already, after you do a compile, this one already, all the, apa ni kita panggil, assembler directive is executed every time you do the compile. So
Okay.
that's why lah kalau you tengok kat sini .org 300, so this line here, this instruction dia now store dekat address 300.
Oh, alright. Understand. Okay. Thank you.
Okay, welcome. So any other question? So we finished our module berapa ni? Module 8 already. Okay, ada stack and then there's subroutine. Okay, the next few slide only for the exercise je lah, kita akan buat exercise. Okay, ada soalan tak? If no soalan, okay, I give you 5-minute breaks, and after that we do exercise. Boleh ya? Okay, so first load IR6. Okay, so this is the program address, which is the address for each of these instruction here. Okay, so load IR16 hi ramen, out SPH R16. So what happens? This one SPH now point to what address? 08, and then load IS R16 low ramen, and then out SPL R16. So SPL will be point to it. We will have value 5F. So automatically you know that the stack pointer point to this address 085F. So this is your stack pointer. T85D, and then this is 085C, and this is 085B, and this one is 085A. Okay, so we finish this one. Up until here, ada soalan tak? Okay, after you initialize the stack pointer, now the stack pointer point to your RAM end. Okay, next, load IR26 with 35. So R26 akan ada nombor 35. Load IR27 with 89. So R27 now will have 89. And last here is load IR2848. Load R2848. Okay, before we go more details here, okay, before we go all of this program here, okay, this question here asks you, okay, to state the content after the assembly program is executed right after the RET instruction. Okay, sampai RET instruction, then you stop. Okay, no need to do the another instruction. Okay, once you execute the RET, then you stop and give the result. Okay, and then okay, we already finished this line here. Load I R28 with 48, and then push R26. So now you're going to push R26 value, put to your stack. Okay, so 35 you put to your stack, and then now the stack pointer incremented by, decremented by 1. Okay, and then you push again R27 to your stack. So R27 is 89. 89 masuk dalam stack, and then whatever is the stack pointer decremented by 1. Now your stack pointer point to address 085D. And then you push one more R28. So what happens is R28 value from R28 you put to your stack, which is 48, letak dalam stack, and stack pointer decremented by 1. So the stack pointer point to address 085C. Okay, next, call modify. Okay, before you go to modify subroutine, you need to what we call here, to put the address, the next address, okay, the next instruction address to your stack. Okay, so the address is 030C. So this one here you can divide it into low byte and high byte. So this address you're going to put, okay, you're going to save to your stack. Okay, so what value that you're going to put first? Is it 03 or 0C? Mana satu dulu kita akan letak? Anyone? Okay, we put the lower byte dahulu to your stack, 0C, and after that followed by 0, 3. And what happened to your stack pointer? Stack pointer now incremented by 2 lah. Okay, so stack pointer point to address 085A. Okay, so now you go to this modify here, subroutine. STS 085D with R27 means that you're going to store value from R27, which is 89, simpan dalam address 085D. Okay, so 085D, current value is 48. Now you store with value from R27. So sekarang dia akan jadi 89. Okay, so the previous value 48 will be replaced by 89. Okay, and then STA 085E. Okay, so you're going to store R28 value to address 085E. So R28, what is R28 value? 48. Now you're going to put it to address 085E. So this one here become from 89 now replaced with 48. Okay, so we finish this one. And then add R28 with R27. So R28, what is R28? 48 plus with R27 is 89, and put the result to R28. So what is the R28 value after you do this addition here? Berapa dapat R28? Anyone? Okay, kamu akan dapat D1. Okay, so D1. Okay, next, RET. So now you're going to execute the RET. Before you execute the RET, what happened? The program counter, okay, will take the value, the address from this tag. Okay, so 030C will be loaded to your program counter. And what happened to your stack pointer? Stack pointer will incremented by 2. So sekarang ni stack pointer kamu point to this address. Okay, yang this address. So this is your stack pointer. Okay, so 1 and 2 incremented by 2. And then next, do you need to do this pop, pop, pop? No need, because you need to stop until the instruction RET is executed. And then you give lah the value. So R26, what is the R26 value? 35. What about R27? 89. R28, okay, no longer 48 sebab kita dah dapat D1 tadi. So you put the D1. Program counter, so this is your program counter value, which is point to address 030C. What about your stack pointer? Your stack pointer point what to what address? 085C. At address, memory address 085B will have what value? 03. This one will have 0C. What about 5D? 5D now become 89. D is 48. And this one is 35. So this is your answers. Okay, you will get 10 marks. Right, any question? Ada soalan tak?
Sir.
Ya, saya.
You mentioned that when you're storing address, right, they will store the lower byte first and then the higher byte, right?
Ya, betul.
But throughout the whole slide, right, it's been saying that it stores higher byte first and then store lower byte. Even in slide 23, it says that higher byte is pushed in first and then lower byte. And then all the example after that is also higher byte first, then lower byte.
Sekejap ya. Wait,
So,
wait a minute.
too far.
Call instruction.
Next one.
Is it? Not this one.
Yeah. The part about the address one. Yeah.
Okay, you see the lower byte is pushed to the stack first. Yang ni.
So our slide is different, sir.
Oh ya kah?
My slide says the higher byte is pushed onto the stack first.
Okay, by right is the lower byte is pushed to the stack first.
Okay.
Okay, so you need to do a correction lah for that slide.
All right. Even in the example,
because the example. Okay, this example here, I already made the what we call here the correction for this example. This example, so I already made the correction.
Okay, all right. Thank you, sir.
Okay. Because if you run this program here, contohlah you run this program to your AVR, you will see it will store the lower byte dahulu and then followed by higher byte. Okay. Okay, sorry because I'm not updating the slide. Minta maaf ya. Okay, any other question? Okay, if no question, then I think we stop here. Okay, and then next class we will do another exercise. Right, this exercise here for the next slide. Okay, thank you, class. Okay, I will upload. Okay, I will give you the latest punya ni lah slide to your WhatsApp group. Okay. Thank you, guys.
Thank you, sir.
Welcome.